Okay, so here's what we were about to talk about last time. We ran out of time. So spherical coordinates. So keep in mind we're talking about new coordinate systems. We already did polar coordinates and cylindrical coordinates. So spherical coordinates has some features in common with cylindrical coordinates, but it is extremely different, and so it's a good idea not to conflate them. So anyway, here we go. Let's talk about what it is. How do we define these spherical coordinates? Known as rho, phi, and theta. By the way, Greek letters and, anyway, so you have to get accustomed to a certain amount of Greek alphabet when you do math. I'm going to start with theta. Good news. The theta angle is exactly what it is in cylindrical coordinates. It's this angle here, measured from the positive part of the x-axis going counterclockwise. Again, just like in cylindrical coordinates. So, so I want to point out that you can think of this, and I suggest you should think of this as defining a half plane, as I have drawn here. Right? So hinged on the z-axis, like so. And the idea is that the point that you're interested in describing, now let me say something that's wrong, and then I'll correct myself. The point that you're thinking of describing is in that half plane, and that's not really quite true. Okay, so moving along, let's see here. So what is phi? Which looks very similar to theta. It's all in the angle of the little line that you put through the O, right? So do be careful to make your little horizontal lines in your thetas conspicuously horizontal, right? And the vertical ones for phi conspicuously vertical. This, kind of 45-degree thing. It's ambiguous. I don't know what it means. So anyway, just make sure your writing is clear. Okay, so what is that? Well, it is an angle measured off of the z-axis. Positive part of the z-axis. Very importantly, toward the theta half plane. So that's why it matters that you think of theta as a half plane. Phi is, at least positive values of phi are measured into that half plane. Okay. All right, so that defines a direction. Now, what, though, happens if phi is negative? And it's exactly what you would expect. If phi is negative, then just go the opposite direction, right? So if this is a positive phi, then as you would suspect, a negative phi would be just back that way, like so. Does that make sense to everybody? Seem plausible? Okay, all right. All right, so perfectly fine for phi to be positive or negative, just like it's perfectly fine for theta to be positive or negative. Okay, all right, moving along. And this is most of it. So once you know your phi and theta, notice that does define a direction coming out of the origin. And once you have a direction coming out of the origin, the only thing that remains is how far do you go in that direction. And again, note the quotes around how far. Again, technically, it's making it sound like it's a distance. And these coordinates do not have to be positive. They are coordinates. They are not distances. Right? There's a little subtle but nagging distinction there. So rho tells you, whoops, what's going on here? Why is my stylus not working? Hello, stylus. Okay, that's disturbing. My finger works, but the stylus. Okay, I'm sorry. I just charged this thing. What's going on? Okay, I don't know why the stylus is all of a sudden not working. So I guess I'll use my backup stylus. And then while I'm doing that, let me plug this in to charge it. Sorry for the problem. Of course I got it. Here we go. I'll plug this into here. And okay, now let's see, does that, yeah, okay, well, it must be a charging thing. Okay, here we go. So So rho measures a coordinate you're going to want to think of as a distance, right? But it measures distance from the origin if rho is positive, thus telling you where you are, right? That gives you this point. That's the point then that's described by these spherical coordinates. If rho is positive. Again, though, you have to worry about what happens if rho is negative. And again, no big deal. It's exactly what you would expect. If rho is negative, just go backwards. And of course, in the same sense, backwards, be like that. Is that cool? So rho, phi, and theta define in this way a point. And any of these coordinates could be positive or negative, and these are the conventions. Okay. All right. So now, how do we relate these to rectangular coordinates? There's a picture that we can draw, and let me scroll down here once I clean up my mess. Here is the picture I'm about to show you is actually a ripoff of what we already have in here. You're going to notice in this half plane. Oh, whoops! In this. Oh, for crying out loud. There we go. In this theta half plane, you see that little triangle, and I'm going to redraw that triangle down here just so we can look straight at it. You really don't have to do this. This is just for kind of aesthetics. I think it's just a little bit easier to visualize what's going on if you're looking directly at it as opposed to, kind of looking at it from some sort of an angle because it's three-dimensional. So looking at this little triangle, and notice that the base of the triangle there, that base is what in cylindrical coordinates we would call R. And easy to observe, of course, that this angle being phi, that makes that angle there also phi. And a little bit of easy trig. Oh, and of course rho being that distance. Some easy trig that allows you to write down a nice, convenient formula for R. So this is our first little foot in the door relationship between spherical coordinates and cylindrical coordinates. Not exactly what we were hoping for. We're trying to connect this to rectangular coordinates. But notice, of course, R figures very prominently in how you convert cylindrical to rectangular. So here it is. R, being that formula, allows me to immediately write down that X and Y are these right here, because after all this now says is X equals R cosine theta, Y equals R sine theta, right? So one little trig observation, and we're 2/3 of the way done with understanding the conversion formulas for spherical coordinates. Everybody on board? Okay. Now, of course, the other is just a matter of looking at the other side of the triangle, right? Z is our remaining coordinate. Well, Z is that leg, that side of the triangle. Also easy trig, and so another easy formula. So really, you get right down to it. All you have to do is understand the trig of this one little triangle, right? Relevant to the picture of how spherical coordinates is defined. One little triangle. And connect a couple of dots, right? But basically, that gives you your conversion formulas for spherical coordinates. So that's how I remember all this stuff, by the way. Very importantly, at least I think it's very important, I've never memorized these formulas, right? And there's a ton of spherical coordinates in the physics major that was my second major in college. Never memorized these formulas. But I understand this picture, and trig is easy. Right? And so as needed, when I need to know spherical coordinate formulas, I think about that picture and then just write them down. Everybody on board? Okay. Now you may be different than I am. If you would rather memorize them, okay, sure, memorize them too, right? But you can't trust your memory, right? Rote disappears eventually. Some people faster, some people slower, but it'll eventually go away. So please do also make sure that you understand that picture. All right. Moving along. Couple of examples. We'll start off with a sphere centered at the origin, and it works out very nicely in spherical coordinates. Big surprise. Easy observation to make from the picture is that x squared plus y squared plus z squared is rho squared. And so notice how close this is to the formula, right? The equation for a sphere centered at the origin. And so rho equals c. Also pretty easy to motivate geometrically. Rho being, at least as long as c is positive, rho being distance to the origin, this just says distance to the origin is constant. And so, of course, sphere. All right. And thus the name spherical coordinates. Okay. All right. I keep hitting the wrong button, apparently. Okay, next example. And this is about the failure of uniqueness. Remember, with polar coordinates are not unique. Cylindrical coordinates, as pretty much just polar coordinates, so also not unique. Likewise with spherical coordinates, except with spherical coordinates it's worse. Other than adding 2 pi as many times as you want, which of course you can always do for any angle, just add 2 pi, it's the same exact. As far as trig is concerned, right, it's all the same. Aside from that, there are kind of 2 different ways to write down a point in polar coordinates. There's the one where the angle is going right at your point, and then there's the one where the angle is going exactly opposite the point and use a negative value of the r coordinate. With spherical coordinates, there are kind of 4. Oh, now this stylus isn't working? Good Lord. Okay, the computer is conspiring. Okay, now my finger's not working either. That is disturbing. I have no idea. Is this one working now? Nope. I'm sorry? Thank you. I was panicking there. Okay, that does. There we go. Okay. But I do have to erase that. Okay. Yeah, so there are kind of 4 ways to do spherical coordinates. And it's because you have 2 different angles, and roughly speaking, for each one of the angles, there are 2 different options, and so you have 2 different options for each of 2 different options. So I want to walk you through some of this, and I'm going to leave the other details to y'all as a nice exercise. So in particular, if we're talking about this point right here, and you see I have the rectangular coordinates indicated there, and that leads to this picture, and there's some easy sort of geometry and trig that y'all can look through. It's marked up. I think that should be clear. And with that said, let's ask, what are the possible values of theta? Well, the point in question, just to sort of, again, get the picture going, we're talking about this half plane. That's the value of theta, pi over 3. So theta could be pi over 3, but I am going to point out that there is also the possibility, right? You could choose to view this in relation to an angle that goes all the way around to the backside, if you will. Right? And you could view this point in relation to that half plane by, well, just imagine phi going backwards away from the dark blue half plane, and thus a negative value of phi. Okay. All right, that's the part I'm going to let y'all think through on your own. Let's talk about the pi over 3 option. So with, let's see here, theta being pi over 3, phi being this angle, which again, we've already done the trig, that angle's pi over 4. Sure, there you go, boom, that's an option. You could have phi being pi over 4. That points you in the correct direction, and once you're pointed in the correct direction, then you just choose your rho then to be positive. And we're in business. So that's the first option for pi over 3, for theta equals pi over 3. The other option is weird, but it's perfectly legal. Let's see, where's my undo? Here we go. perfectly legal. And that is to say, look, this direction here is exactly opposite of this direction, which I could think of as a negative value of phi, right? So again, now the temptation is to think of this as positive phi going, well, toward the theta half plane as it's supposed to, right? But instead, if, let's see, I don't have the flexibility for this. Instead of like that, positive value of phi, you go backwards, right? And then that's a negative value of phi. So this right here would be pi less than the pi over 4 that we're looking at. And so this value of phi here would be negative 3 pi over 4. Everybody follow that? Which is weird and undesirable because, for one thing, it gets you pointing in the wrong direction, right? So our point is here in purple, we're now pointing that way, but it's not just a wrong direction, it is exactly wrong. And so we can get to the point in question now with a negative value of phi, of rho. Yeah. Does that make sense to everybody? So, nice exercise. Think about now, how would everything change, and all the little details are going to change, if you had 4 pi over 3 for your theta instead of the pi over 3 that we've been looking at here. It's a good little mathematical weightlifting thing, so I hope you all will give that a shot. And let's see here, moving along now. Let's see here, okay. There's a lovely observation to be made relating spherical coordinates to longitude and latitude, right? And I hope everybody is accustomed, at least somewhat, to the idea of longitude and latitude on the surface of the Earth. I'm going to use the word longitude to refer to east longitude specifically. So measured eastward from the convention is what do they call it, the prime meridian or something like that. So that's what I'm just going to call longitude. And then latitude, again, I'm going to use the word latitude to refer to north latitude measured northward from the equator. Okay, so again, in this discussion, longitude always means east. If I want to go west, I'll say it'll be a negative value, right? And latitude is always measured northward. If I want to go southward, it'll be a negative value. Okay. So a couple of nice observations to make here. For one thing, if you set up the globe with the North Pole being on the positive part of the z-axis and the positive part of the x-axis going through the prime meridian and centered at the origin, blah, 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 as figured. Beautiful fact then, again, I don't know why that's doing that. A beautiful fact is that, I keep hitting the wrong buttons. Longitude is theta. You can see it right there in the picture, right? It's exactly this. What I have in green, dark green here is exactly how we define the theta angle. And then likewise, let's see here. Likewise, this latitude, well, now that's not phi, not exactly phi. Phi, by contrast, phi is measured that way, like so, but what we can see from this, eraser, sorry. What we can see from this then, oh my gosh, I don't know how that happens. What we can see from this is that even though these are not the same angle, they add up to pi over 2. And again, you can see it in the picture, right? And the further north you go, the greater your latitude is, the lower your phi is, and the further south you go, the greater your phi is, and the less your latitude is, and they just always add up to this same constant value. So nice, easy relationships then between these variables and map coordinates, longitude and latitude. Is everybody on board? Okay. So who cares? Last little detail, of course, is that rho is always the radius of the Earth, which we're going to treat as a constant, even though it isn't really quite technically. Or I don't know if y'all are aware of this, but because the Earth is rotating, it's actually kind of slightly flat. Right? It kind of bulges out at the equator to the tune of something like 20 miles. It's substantial. You'll never notice it because the Earth is like 4,000 miles radius, right? But it's still, nevertheless, non-trivial. Okay. Alrighty. So what is this useful for? Aside it being, I don't know, arguably a memory tool. And what it is useful for is, for example, the following. Suppose you're interested in describing a point on the Earth. How do we talk about where points are on the Earth? Longitude and latitude, right? So if you know the longitude and latitude, the observations that we just made above allow us to immediately write down the spherical coordinates. Just boom, nothing to it. The observations on the previous page allow us to immediately write that down in rectangular coordinates. Now I have the rectangular coordinates, at least according to this setup, rectangular coordinates of any point on the surface of the Earth. Why does that matter? Well, because with rectangular coordinates known for 2 points, it's super easy to compute the dot product. Right? This dot product is in rectangular coordinates. The dot product super easy, right? It's just x1, x2 plus y1, y2 plus z1, z2. Nothing to it. Why does that matter? Well, because dot products have a geometric interpretation, and the radius of the Earth is known, and that means that given two locations, I can then solve for this angle, the sort of the central, at the center of the Earth, central angle between 2 points. And once you know that angle, then of course a little bit of super easy geometry tells you what the distance is along the surface of the Earth. And it's a pretty non-trivial problem otherwise. If you take away this observation and you give yourself 2 points on the surface of the Earth and you want to know, how far is that? Right? Which, by the way, big problem, very important problem. Airlines have to deal with this, right? They need to fly from New York to Moscow often, or New York to Oslo or whatever, right? And you don't want to have to fly along a latitude line and then take a sharp right turn and go up along a longitude line, right? That'd be way more miles. It burns more fuel. The economics of that are unsustainable. It's just a huge, huge problem, right? So we want to know how to get exactly, fast as possible, shortest distance between 2 points. And again, otherwise, a pretty hard problem, right? If you were thinking in terms of like the Mercator projection, like the flat map thing, the shortest distance does not look like a straight line. What that curve is, and this gets you right on it much more easily. So neat little application there. Okay, yeah.
How would is there a mathematical relationship between Mercator projections and spherical coordinates? Is there a way to relate them?
I haven't thought about that in a long time. I'm sure there are. Yeah, bound to be, right? We'd have to think about exactly how to write down that picture, and there's going to be some little detail devils involved. But yeah, I feel sure there are. But yeah, off the top of my head, I don't know the details. Yeah. All projections basically are bad, right? People rightly don't like the Mercator projection, and there are all these different alternatives. They have their own faults in various different ways, and they're all bad in some sense because ultimately the Earth is curved, and curved things are not well represented by not curved things. It's just a reality, right? So if you really want an accurate representation of the Earth, what you need is a globe. They just don't fit well on computer screens. So anyway. Okay. All right. Converting equations, it's a lot like the other coordinate systems we've talked about. For example, if you want to take this equation for a sphere, and if you want to write it in spherical coordinates. Now, quick side note, why would we ever want to do such a thing? Turns out we're going to be doing this kind of thing a lot. It's hard for me to sort of foreshadow it well here, but there's going to be many circumstances where spherical coordinates are way more desirable than rectangular coordinates. I mean, importantly, with it'll make your life much better to be able to do things in spherical coordinates, right? But it's easy to write down, an equation of a sphere in rectangular coordinates, right? We have previous familiarity with that. So you basically just plug in the relationships, and there is your resulting equation of a sphere in spherical coordinates. Now, a little tip and trick here, just as a reminder, is that you don't have to immediately plug in, for example, again, I almost scared myself again. This x right here, you see I plugged in the formula for what x is in spherical coordinates. You don't have to do that immediately. Sometimes, such as in this case, it's really helpful to first square out your square, right? Get all your terms visible. And once you have all your terms visible, you might get lucky, as I did here, and you might find that, oh yeah, look at all of that stuff. I can just immediately write that down as rho squared, and we just saved ourselves a bunch of trig. Yeah.
So if you're integrating with this, does that mean each rho was constant and simplified that way?
So huge question, what do you mean by integrating with this, right? So that's actually going to be a big topic, and how you use spherical coordinates to actually do integrals, and what is an integral in multiple dimensions. There's multiple lectures worth of stuff that we have to say before we can make sense out of that. Yeah. So I'm not going to be able to answer that question. It's way too much. Yeah. So we will get to that in chapter 5, in the sort of the later end of chapter 5. Yeah. All right. Okay. So moving along. Good news. This business about standard basis vectors. Y'all remember, of course, the usual standard basis vectors. You might have previously seen them commonly written as IJK, and y'all may remember as well that I personally prefer to write them as E1, E2, E3 because it generalizes so much more nicely, and that pays off in several different ways. So these are the rectangular standard basis vectors. But you can also just, again, I don't know how that's happening, but okay, so you can just as well talk about standard basis vectors for other coordinate systems. So the idea is, wherever you might happen to be, whatever point you're looking at, let's say this point right here, we're thinking about polar coordinates, what is the unit vector that points in the direction where only the single polar coordinate r is increasing? Theta is constant. So you notice in the direction of this green arrow here, theta is not changing as I move in that direction. Only r is changing. And so I have a unit vector representing what happens when I'm changing only the r coordinate. And then likewise, what's the deal with this vector right here? Well, that vector, at least at the instant that I'm at this point, if I am moving in that blue direction, at that particular instant, r is not changing because I'm going perpendicular to the r line there, if you will. So theta is changing, but r is not. So between them, two of them, this pair of vectors here is a kind of a reference frame, you might say. It's a natural set of vectors with respect to which it would, we can easily talk about, directions and velocities when you're in polar coordinates. And there are some situations where that can be useful. Now, I will say, and in leading up to something else here, those situations where this is useful, I don't really think are going to come up in this course. So I'm not going to spend a lot of time on them. There are formulas for these polar standard basis vectors. And that's a nice little geometry exercise. Again, a little bit of mathematical weightlifting. If you want to think through for yourselves why are these the correct formulas for those vectors, it's a nice exercise. Go ahead if you like. But I think a reasonable position for us to take is it's important for you to know what they are. Like, what do you mean by a standard basis vector in polar coordinates? Well, this is what we mean. And to know that there are formulas that can be easily found that will tell you how to write them down in rectangular coordinates. Okay. So likewise cylindrical, likewise spherical, and again a bunch of little details that we shouldn't get bogged down in. Again, I don't see this as coming up in this course to speak of, if at all. Okay. Couple of things to know though, and again, I've already pointed out that there's a lot of things that are super awesome about rectangular coordinates. There's a reason that we do most math in rectangular coordinates. And we have to let go of those when we're in other coordinate systems. So one of them is, while the standard basis vectors in rectangular coordinates are constants, not in these other coordinate systems, right? They move around depending on where you are. So that's a disappointment. You don't get sort of nice conveniences such as, like here, it's just basically a given that if you have a point with rectangular coordinates, then, okay, well, that tells you how to write it as a combination of standard basis vectors. This works great in rectangular coordinates. In other words, with rectangular standard basis vectors. Nothing of the sort works in any other of the coordinate systems that we've talked about. So you just have to deal with the disappointment. Nevertheless, there are places where these can be useful. Again, I want you to be aware of their existence. Okay. All right. We're going to move on now to Chapter 2. And there's a bunch of terminology that has to get, I'm going to say, said. But really, in fact, I'm going to wave my hands at a lot of this because that's perfectly readable, right? I do want to hit the highlights, so I want you to know what the purpose is. And let me skip ahead real quick. I'm going to come back to this page, but I want to skip ahead to the examples on the next page. And notice what we're going to be talking about is whether a function is or is not invertible. Now, this is important, right? If you want to be able to talk about the inverse function, which can be really useful, right? Really importantly useful. Well, you can't even talk about the inverse function if the function isn't invertible, right? So we need to be able to define what we mean by invertible, and there are sticky wickets on that have to be addressed and thought through carefully. So that is going to be our incentive for much of what is on the previous page here. And so first thing I want to emphasize is what a function is. It's a commonly misunderstood thing. It's kind of okay in high school algebra classes, most of the time. If you take a really carefully done single variable calculus class, it'll be important to understand this distinction. And in this class here, it's actually significantly important. But anyway, here we go. A function is not just a formula. It's a common misunderstanding. A function is a trio. It's three things altogether. You need to know all three of the things to have a well-defined function. And what it is these three things right here. You need to have a well-defined space where the inputs come from. We call that the domain, typically. You need to have a well-defined space where the outputs go into, commonly called the target. Some people like to call it codomain. I don't know, to me that seems weird. Target to me makes sense. I mean, if you're shooting arrows at a target, well, the target is where the things land, right? It just seems like a natural thing to call it. And then the third thing, and again, what people typically think of a function as being the formula, you might say, the thing that tells you what how to compute the output value for a given input value, and to avoid any suggestion that it has to be written down algebraically, we don't call it the formula in practice, or not strictly anyway. We call it the rule of assignment. Very often a formula. Okay, so a function is a trio. If all you know is the rule of assignment, technically you don't really know what that function is. At least there are some issues that have to be worried about. Okay, so a couple of examples. Let's see here. And before I get into this, let me, fingers crossed, hope that my stylus here has gained enough charge. So weird. And nope.
You're on eraser.
I am on eraser. Thank you. Okay. All right, so that's working now. Okay, and now I better plug this little thing back in because its charge is not good. Okay, so here's an example. I'm going to talk, well, first thing I'll point out, the natural log, still on eraser. Thank you. I appreciate the reminders. You're saving me confusion. Okay, so the natural log function. And a lot of people think, okay, log, yeah, that's the thing with the exponents and stuff, right? Okay, that's the formula. That's the rule of assignment. As a function, I need to know first, what's the domain? Where are you going to claim that your function is defined? For what input values is this defined? What input values can you plug into this function? Next, what kind of critters are your outputs going to be? Are the outputs real numbers, as in this case? But hey, outputs could be a matrix. The output could be a vector in R3. What kind of thing is it that comes out of this function? So it's this trio that is the function. Right? This is the domain that I like to think of as the input space. This is the target that I like to think of as the output space. And this is the rule of assignment, the formula. Okay. All right. Okay. Here's another one. What I'm going to call the student ID function. All three of these functions here have the same rule of assignment. For whatever student you're asking about, the value of the function is what is that student's student ID number. Okay? So it's not a formula, you'll notice, but it is a perfectly well-defined rule of assignment because for any given input, there is a corresponding unambiguous output. Okay? Now, why do I have three different functions listed here with three different names? Well, it's because these are three different functions, because keep in mind, a function is not a formula. A function is a trio. And these two functions right here, they have the same rule of assignment. They have the same domain, but they have different targets. Right? So now, it seems silly. Student ID numbers are all integers, right? Why would I be so silly as to let the rule of assignment be this collection of all real numbers? That seems ridiculous. But it remains that every student ID number is a real number. So there's really nothing wrong with this G function. Yeah, it's got a bunch of extra space in the target that's not going to be used. But so does F, right? Z has got way more numbers in it than are actually realized by student ID numbers. No student has a 756 digit student ID number. Right? So this too is bigger than it needs to be. So whatever. Okay, so F and G, different functions. And then likewise, let's see here, G and H. different functions. And in addition to having different targets, they also have different domains. All right. Fussy. You'll see in a minute why that's important. A little bit of terminology. We use the word image to describe the set of actual outputs from the function, not the set where the outputs land, but the set of the actual outputs. Right? So a nice, easy example to see the distinction. I can talk about this function right here. There's a function. I've got a domain, I've got a target, and I've got a rule of assignment. In this case, a formula. A perfectly reasonable function. What is the image of this function? What are the actual outputs? What really comes out of this function? Well, it's only the positives and 0, right? So non-negative numbers, non-negative reals are all that actually comes out of here, right? So the image is this right here, not the same as the target, which is all reals, right? So that's the distinction. The image is not up to you. You don't get to choose what the image is, right? The image is what it is. The target, there's a lot of flexibility. I made the target here R. By the way, why did I make the target here R? It was easier to write down. I just needed to know what kind of things are coming out, and I didn't want to have to sit down and think about, wait a minute, what are the actual output values, and let me do an optimization problem and figure out what is the minimum to come out of here, and try to get precise about what's the smallest that this could actually be. I don't need that, right? Very often it's perfectly fine and satisfactory just to know what kind of critters are coming out, and that's it. Right? So anyway, make sure to distinguish between the target and the image. They are not the same, and it is important. Okay. All right. A little bit more terminology. I'm getting ahead of myself. When you have a rule of assignment and an input goes in and an output comes out, we use the term image for that single output value. It's a different usage of the same word. The image of a function is the set of all outputs. The image of a single input is that appropriate corresponding single output. So again, both usages of image refer to outputs. But I hope this is a reasonable terminology choice. The input that gave a given image is called the pre-image. You can think of this as that when I plug into the function, what comes out is the image. But if I know what comes out and I want to determine what was the input that it came from, in some sense you're kind of going backwards through the function, if you will. And so anyway, pre-image is a term intended to represent that. Yeah?
If you already know what your image is, can you make that your target?
Yes. Yeah. That's perfectly reasonable. Yeah. And there might even be, let me say this. There are definitely some situations where that's useful, and we're going to see one in just a minute. Yeah. Thank you. Yep. But, yes, so you may, but you don't have to. Yeah. Okay. All right. A little bit more terminology. Just a lot of ideas that have to be talked about and thus defined. I've represented here figuratively some functions. For each one of these, there's this figurative input space and this figurative output space. Typically, we don't have domains that only have 3 elements in them, right? And targets that only have 3 elements in them. But just for sort of drawing purposes, this is very convenient for what I need to do. For each one of these functions, and for any function in general, you can ask the following two questions. Is it the case that every point in the target, let's start with this one here. There's a point in the target for that function. Does every point in the target have at least one pre-image? Well, again, for this point that we've picked there is only one pre-image, and there it is. So now let's think through, though. Is it the case for every point in the target? Is there at least one pre-image? Well, this one has one pre-image. This one has two pre-images. Let me highlight accordingly. For this point here, we have two pre-images, which you'll notice is at least one. And then likewise for the last one. The last one has one pre-image. So here, what we call surjective or onto, this function satisfies the rule because every output has at least one pre-image. Notice not every function does. This function does not. Because while some of the points have at least one pre-image, this sad little fellow over here does not, right? Nobody's visiting this guy, right? So this, you see this bottom point here, right? It's not the image of anything. It has zero pre-images, which is not at least one. Everybody okay? Seems a weird thing to want to talk about. Ends up being important. Injective, aka one-to-one, which is an unfortunate term. I prefer to say injective, is the condition where every point in the target, let's take, for example, that point there. Every point in the target has at most one pre-image. So again, let's kind of think it through, and let's just kind of go down the list. This point has one, that is at most one. This point here has one, that is at most one. This has one, that is at most one. This has zero, which is at most one. Right? So this function here, it wasn't surjective, but it is injective. So anyway, nice little distinction between every target point having at least one or at most one pre-image. And notice that some functions have both injective and surjective, both of the jectives, aka bijective. And of course, if you think about it, if you have at least one and at most one, that means you must have exactly one pre-image. Okay, all right, so let's talk about why this matters. And it has to do with invertibility. Again, I foreshadowed that. We're going to come right to it in just a moment. If you want to talk about the inverse function, for example, if I want to take this function where we were going sort of left to right, domain here, target there. If I want to talk about the inverse function would have to go this way. And so I would need to know that for every point in what is now my domain, right, formerly the target, but now the domain, for every one of these points, I need to know that there is exactly one what we formerly thought of as pre-images, but what we now are going to think of as images, right, for my inverse function. Because this is what a function is, right? If you want to talk about a function for every input, there has to be exactly one well-defined output, whatever kind of critter that output is, whatever, but there needs to be exactly one output. And so notice we need both injective and surjective for that to make sense. I cannot invert this function. I don't know how to define what the value of the inverse function would be at this point. It doesn't have any pre-images that I could call the inverse function image. So not invertible. right? And then analogously, of sorts, this is not invertible because this point right here, if I'm going to talk about the inverse function of this function, well, I need to know the output value for that point. Well, is it this one or that one? Could be either. It's not clearly, unambiguously defined what the inverse function should be for that point. So again, not invertible. And of course, this one over here is just it's doubly not invertible, right? It's all sorts of problems. And what you really need is something like this. Injective and surjective. Every output had exactly one input. Allows me to define an inverse. So notice now we can see why all this stuff over here is important. If you just casually speaking write this down and then you say, oh yeah, I want to talk about the square root function being the inverse of x squared. No, it isn't. This function here says R is my domain and R is my target. If you say you were going to invert this function, you're claiming that you can compute the square root of every real number and have a result that is a real number. And no, you can't. So this function here that I have highlighted in yellow, not invertible. Really importantly, not invertible. You're going to accidentally write down a bunch of absolute nonsense if you go around talking about this as being an invertible function. It just is not. However, easily resolved. Notice if we just change the domain to be just the non-negatives, change the target to be just the non-negatives, no problem. This function perfectly invertible because square root, what I want to call the inverse of this function, okay, well, for every non-negative real number, I can compute a unique, perfectly well-defined non-negative square root. And everything's fine. And no nonsense. So this function is invertible. Is everybody with me? All right, so that's why we care, and we're out of time, so we will draw a line right here and see y'all later. Have a good one. See you on Wednesday.